Find somewhere comfortable. You don't need to follow any of this closely. You don't need to remember a single word. Just let the sounds arrive, and if they carry you somewhere quieter before we've even begun, that's exactly right. We're in no hurry tonight. If today was hard, and for many of us, it was, in ways large or small or simply accumulative, you can set it down now, not forever, just for this. The day has already done what it was going to do. It's behind you now, growing more distant with every breath. Tonight we're going somewhere very far away, a place where the air is so dry it barely registers as air at all, a place where silence is not the absence of something, but the presence of something older and deeper than almost anything else on Earth. A strip of land along the western edge of South America, pressed between the Pacific Ocean and the highest mountains on the continent, where rain is not merely rare but essentially absent, where the ground has been dry for longer than most of the world's mountain ranges have existed. We're going to the Atacama. You don't need to picture it clearly. You don't need to hold the geography in your mind. Just let the words come and let them drift past you the way clouds drift past a mountain. Slowly, without effort, leaving a faint trace of something behind. The Atacama has been waiting a very long time. It can wait a little longer while you settle. Close your eyes if they aren't already. Let your body grow heavy, and let's begin. There is something about the word ancient that we use too casually. We call a building ancient if it was constructed 1,000 years ago. We call a forest ancient if its trees have been standing for 5 centuries. But the Atacama Desert requires a different kind of ancient entirely, one that asks us to reach back, not through human history, not through recorded civilization, but through the deep, slow calendar of the Earth itself. The Atacama has been a desert in some form for approximately 150 million years. Sit with that number for a moment. Dinosaurs were at the height of their dominance. Not the creatures that would later be made famous by their extinction, but their predecessors and contemporaries, enormous animals moving through landscapes that no longer exist in any recognizable form. Something patient, something that would outlast almost everything around it. The semi-arid conditions that characterize the broader Atacama region stretch back across that full span of time. But the hyper-arid core, the inner desert, the true heart of the place, solidified into something more extreme at least 15 million years ago, and possibly as long as 33 million years ago, during a period geologists call the Middle Miocene or the earlier Oligocene epoch. 33 million years is the outer estimate, and 15 million years is the more conservative one. Either figure makes the Atacama the oldest desert on Earth by a considerable distance. To understand what hyperid actually means, it helps to start with what ordinary dryness looks like and then keep going. A desert, technically, is defined as any region that receives less than 250 millimeters of rainfall per year. The Sahara, which most people picture when they think of desert, receives roughly 25 millimeters annually across much of its extent. That already sounds vanishingly small. The Atacama's overall average is around 15 millimeters per year. And in the hyper-arid core, the central valleys and plateaus where the deepest silence lives, the figure drops to somewhere between 1 and 3 millimeters annually. Some weather stations in this region have operated for decades without recording a single measurable rainfall event. There is historical and geological evidence suggesting that certain areas received no significant precipitation between the year 1570 and the year 1971, a span of more than 4 centuries. Not a drought, simply the ordinary state of things. At 1 to 3 millimeters of rainfall per year, something extraordinary happens to the chemistry of the landscape. And to understand it, we need to think about water not as something that falls from the sky, but as a participant in chemical reactions. Ordinary weathering, The process by which rocks break down, minerals dissolve, and landscapes slowly transform requires water. Not in large quantities, but in some quantity. Water molecules are chemically active. A water molecule is made of one oxygen atom bonded to two hydrogen atoms, and the way those atoms are arranged gives the molecule a slight electrical asymmetry. The oxygen end carries a faint negative charge. The hydrogen ends carry faint positive charges. It dissolves salts by tugging on the positively charged ions of sodium and the negatively charged ions of chloride, separating them and carrying them away. It participates in the slow acid-base reactions that dissolve limestone and granite over geological time. It carries the products of these reactions downhill, into rivers, into the sea. In the hyperarid core of the Atacama, water molecules are so scarce in the air and on the ground surface that these reactions essentially pause. Not stop entirely, nothing in chemistry is perfectly still, but slow to a rate so glacial that the landscape effectively freezes in time. Rocks that would have crumbled and dissolved in a wetter environment sit intact for millions of years. Mineral deposits that would have been leached away by groundwater remain concentrated where they formed. Soil chemistry that would have shifted through repeated cycles of wetting and drying holds its composition across geological epochs. This is why the Atacama is sometimes described as a slow-motion fossil. The landscape itself is preserved the way a body might be preserved in very cold, very dry conditions, not by any active process, but by the simple absence of the agent that would normally cause change. The geography that contains all of this is worth holding gently in the mind. Picture a strip of coastline running roughly north to south for about 1,600 kilometers, roughly the distance from London to Athens or from New York to Miami and halfway back again. This strip is pressed between two vertical walls. To the west, the Pacific Ocean. To the east, the Andes Mountains, whose peaks in this region rise to over 6,000 meters. The Atacama Plateau itself sits at an average elevation of around 3,000 meters above sea level, already higher than most of the Alps, higher than the base camps of many Himalayan expeditions. The air at this altitude is thinner, drier, and colder than the air most of us breathe every day. Within this strip, the landscape is not uniform. There are valleys so flat and pale they look like the surface of another world. There are salt flats, called salaries, where the ground is a blinding white crust of crystallized minerals stretching to the horizon. There are volcanic peaks rising above the plateau, still geologically active, their flanks dusted with sulfur deposits in shades of yellow and orange. There are river valleys, or rather the ancient remnants of river valleys, carved when conditions were wetter, now dry and still, their shapes preserved by the same absence of moisture that preserves everything else. Some of these valleys have soil chemistry that has barely shifted since before the Andes were fully formed. The Andes, geologically speaking, are a relatively young mountain range. They rose to their current height primarily over the last 10 to 20 million years, pushed upward by the slow collision of the Nazca tectonic plate sliding beneath the South American plate. Moisture from the Amazon basin could travel further west. The desert was drier than the surrounding regions, but not yet the extreme environment it would become. As the mountains rose, they cut off more and more of the moisture that had been arriving from the east, and the hyper-arid core deepened and intensified. Yet even in the valleys that predate the full height of the Andes, the soil tells a story of almost unbroken dryness, minerals that would have been washed away by rainfall. Nitrates, perchlorates, sulfates are still present in concentrations that would be impossible in a wetter environment. They are simply sitting there, patient and undisturbed, the way they settled millions of years ago. There is something almost meditative about that. A landscape that does not rush. A landscape that has been practicing stillness for longer than our species has existed, longer than mammals have dominated the earth, longer than the extinction event that ended the age of the dinosaurs. It kept being old quietly, while the world around it rebuilt itself. And it is still here, still dry, still patient, still old in a way that the word ancient doesn't quite reach. The stars above it are the same stars, moving through the same slow arcs. The silence in its deepest valleys is the same silence. And tonight, from wherever you are lying, that silence is available to you, not as a place to travel to, but as a quality to carry gently into the hours ahead. If you were to design, from scratch, the driest place on Earth, if you were given a blank map and asked to arrange geography, ocean currents, and atmospheric pressure systems to produce the most extreme aridity possible, you would be unlikely to improve on what nature has assembled over the western edge of South America. The Atacama does not owe its dryness to a single cause. It owes it to three separate mechanisms, each powerful enough on its own to produce a very dry environment, and all three operating simultaneously, reinforcing each other, stacking their effects like locks on a door that rain cannot open. It is worth working through each one carefully, not because you need to memorize them, but because each one is a window into how the atmosphere actually works. How air behaves, how water moves, how pressure and temperature and ocean temperature conspire in ways that feel almost deliberate. The first lock is the Andes. The Andes Mountains form one of the longest and highest continuous mountain chains on Earth. Along the stretch that borders the Atacama, their peaks routinely exceed 5,000 and 6,000 meters. To the east of these mountains lies the Amazon Basin, one of the wettest regions on the planet, a vast green system that evaporates enormous quantities of water into the atmosphere. That moisture-laden air moves westward, pushed by the prevailing trade winds until it encounters the wall of the Andes. When air meets a mountain range, it has only one option: go over. And as air rises, something fundamental happens to it. The atmosphere exerts pressure on everything below it, the weight of all the air above pressing down. At sea level, that pressure is relatively high. As you climb, there is less air above you, so the pressure drops. When a parcel of air is forced upward by a mountain slope, it moves into a region of lower pressure, and lower pressure allows gas to expand. And here is the key: when a gas expands, it cools. This is not a mysterious phenomenon. It is a direct consequence of the way gas molecules behave. When a gas is compressed, the molecules are pushed closer together and they collide more frequently, generating heat. When a gas expands, the molecules spread apart. Collisions become less frequent and the temperature falls. So as the Amazon's moist air rises over the Andes, it cools. And cooling air has a reduced capacity to hold water vapor. Water vapor in air exists as individual molecules moving freely among the nitrogen and oxygen. As the temperature drops, these molecules slow down and begin to cluster together, condensing around tiny particles of dust or sea salt to form droplets. Those droplets form clouds. The clouds build and thicken, and eventually the droplets grow heavy enough to fall as rain or snow. This rain falls on the eastern slopes of the Andes, the windward side, the Amazon side, in tremendous quantities. The mountains wring the moisture out of the air, the way you might wring water from a cloth. By the time that air crests the mountains and begins descending on the western side, the Atacama side, it has lost most of its moisture. And now the same physics that cooled it on the way up work in reverse. Descending air moves into regions of higher pressure. Higher pressure compresses the gas. Compressed gas warms. So the air arrives on the western side of the Andes, not only dry, but warming, growing even less likely to produce rain as it descends, because warm air can hold more water vapor without condensing, and there is very little water vapor left in it to condense anyway. This is the classic rain shadow effect, and by itself it would produce a fairly dry region west of the Andes. But the Atacama is not merely fairly dry. Sitting over the southeastern Pacific Ocean, at roughly 25 degrees south latitude, is a vast semi-permanent feature of the atmosphere called the South Pacific anticyclone. An anticyclone is a high-pressure system, a region where air pressure is above average. The word anticyclone simply means that the air circulation runs in the opposite direction to a storm system. In the southern hemisphere, the air spirals clockwise outward from the center rather than counterclockwise inward as it does in a low-pressure system. But the most important thing about the South Pacific anticyclone is not its rotation. It is what is happening vertically within it. High-pressure systems are defined by descending air. Air is sinking from higher in the atmosphere down toward the surface. And we have already established what happens to descending air. It compresses and it warms. Warm, descending air does not want to form clouds. To form a cloud, air needs to rise, cool, and allow its water vapor to condense. Descending air is doing the opposite. It is warming, which means its capacity to hold water vapor without condensing is increasing. Any moisture present in the air becomes less and less likely to condense. Cloud formation is actively suppressed. Rain is not merely unlikely, it is mechanically prevented. The Atacama sits directly beneath the influence of this anticyclone. The descending, warming, drying air of the high-pressure system presses down on the region, adding a second layer of suppression on top of the rain shadow already cast by the Andes. Even on days when some moisture might find its way into the region from other directions, the sinking air of the anticyclone tends to dissolve any clouds that try to form. Why does this anticyclone sit where it does? The answer lies in the global pattern of atmospheric circulation. Near the equator, the sun heats the surface intensely. Warm surface air rises, creating a band of low pressure near the equator. That rising air eventually reaches the upper atmosphere where it spreads north and south. As it moves away from the equator, it gradually cools and sinks back down, and it tends to sink at roughly 20 to 30 degrees north and south latitude. This is where the world's major subtropical high-pressure systems form and why the great deserts of the world, the Sahara, the Arabian Desert, the Australian interior, and the Atacama, all cluster in these latitude bands. The Atacama, at roughly 20 to 25 degrees south, sits squarely in this descending air zone. Two locks, then, the rain shadow of the Andes and the sinking air of the anticyclone. Either one would make this a dry place. Together, they create something extreme, but the third lock is perhaps the most elegant of all. Running north along the coast of Chile and Peru, close to the shore, is the Humboldt Current, sometimes called the Peru Current. It is a river of cold ocean water flowing northward from the subpolar regions of the southern Pacific, and it is cold in a very specific way. The coldness of the Humboldt Current is not simply a matter of where it comes from, though that contributes. It is primarily driven by a process called upwelling. The prevailing winds along this coastline blow roughly northward and offshore, pushing the surface water of the ocean away from the coast. When surface water is pushed away, something must replace it, and what replaces it is water drawn up from the deep ocean. Water that has been sitting in the cold, dark depths, far below the reach of sunlight. Sea surface temperatures off the Chilean and Peruvian coast can be as low as 16 degrees Celsius in regions where, based on latitude alone, you might expect temperatures closer to 25 degrees. Now consider what happens when warm, humid air from over the open Pacific moves toward this coast. It passes over the cold surface of the Humboldt Current, and the cold water chills the air from below. Cold air is denser than warm air. The molecules are moving more slowly and pack more closely together. This dense, cold air near the surface cannot rise easily. Above it sits warmer, lighter air. The result is a temperature inversion, a layer of cold air trapped beneath warm air, like a heavy blanket pinned down by something pressing from above. A temperature inversion is an almost perfect barrier against rain. For rain to form, air must rise, cool, and condense. In an inversion, the air near the surface cannot rise. It is too dense, too cold, and the warm air above it acts as a lid. Convection, the churning upward movement that drives thunderstorm formation and most rainfall, is suppressed. The moisture that is present in the marine air stays locked in the cold layer near the surface, unable to rise and unable to fall as rain. What it can do, and this is important, and we will return to it, is form fog. Dense, low, persistent coastal fog. And this is important, and we will return to it. The Atacama's fog, called Camanchaca, is the direct child of this temperature inversion. It is moisture that made it to the coast, but could go no further, caught between the cold ocean surface and the warm air above, and so it simply stays, a grey presence rolling in from the sea each morning, carrying life with it in the only form the desert allows. But that is for the next chapter. For now, consider the full picture of the three locks together. The Andes strip the Amazon's moisture from the air before it can cross to the west. The South Pacific anticyclone suppresses any cloud formation by filling the region with warm, sinking, drying air. And the Humboldt Current chills the marine air so completely that it cannot rise, cannot convect, cannot produce rain even from the moisture it carries. Any one of these forces would make this a dry environment, all three operating together, reinforcing each other across an area of over 100,000 square kilometers, produce something that is less a desert in the ordinary sense and more a kind of atmospheric vault, sealed against moisture from every direction. The result is an average annual rainfall of around 15 millimeters across the broader desert. In the hyperarid core, that drops to 1 or 2 millimeters. Some years, in some valleys, the rain gauge records nothing at all. The soil stays dry. The rocks stay dry. And the air above it stays clear. So clear, as we will discover much later tonight, that it has become humanity's best window onto the deep universe. But that clarity is earned through absence. Through the three locks holding firm, year after year, decade after decade, for 15 million years and counting. The Atacama receives almost no rain. This is the fact that defines it, the fact that shapes everything about it. But there is a quiet exception. Not to the rule exactly, but alongside it, a form of moisture that finds its way into the desert, not from above, but from the side, not as rain, but as something softer and stranger. The local name for it is Camanchaca. It translates roughly as the fog that suffocates. But that translation misses something. The Camanchaca does not suffocate. It nourishes in the only way this landscape permits. To understand the Camanchaca, we need to stay for a moment with the temperature inversion we just described. That layer of cold, dense marine air trapped beneath warmer air above it, created by the Humboldt Current, chilling the air at the surface of the sea. This inversion is the reason rain cannot form along the coast. But it is also the reason fog can. The difference between fog and rain is simply a matter of scale. Both involve water droplets condensed from water vapor, but rain droplets are large, typically between 0.5 millimeter and several millimeters in diameter, heavy enough that gravity pulls them down through the air faster than the air can hold them up. Fog droplets are tiny, often only 10 or 20 micrometers across, which is roughly 1/5 the width of a human hair. At that size, the droplets are so light that the faintest upward air movement keeps them suspended. They drift rather than fall. They are carried by the air rather than falling through it. When the cold marine air over the Humboldt Current is pushed gently on shore by the prevailing winds, and this happens most reliably in the morning hours, when the temperature gradient between sea and land is at its greatest, it brings its fog with it. The Camanchaca rolls inland in long, dense banks, grey-white and low to the ground, moving slowly like something that knows it is not supposed to be here and is trying not to draw attention to itself. It travels inland, but only so far. The Chilean coastal range, a chain of hills and low mountains running parallel to the shore, rising to roughly 800 to 1,000 meters in this region, acts as the second barrier. Most of the Camanchaca cannot climb over the coastal range. It presses against the western slopes, thick and cool, and then it stops. The valleys and plateaus of the interior Atacama remain beyond its reach, but the slopes and ridges of the coastal range and the narrow zone just inland of it receive the fog with something like regularity. On some mornings, the fog is so dense you cannot see more than a few meters ahead of you. On others, it is a thin, luminous haze, filtering the early light into something soft and directionless. Now consider what happens to that fog when it meets a surface, a rock face, a cactus spine, a strand of spider's silk. The individual droplets, too light to fall on their own, collide with the surface and cling to it. More droplets arrive and join them. The cluster grows, and eventually, when enough droplets have merged, the collected water is heavy enough to run, to move downward along the surface, pooling in crevices, dripping from the tips of spines, trickling into the soil. Not through any dramatic transformation, but through simple accumulation, the patient gathering of individual droplets too small to matter alone, until together they are enough to sustain life. This process is called fog drip, and it has been exploited, first by evolution and then by human engineering. The plants that live in the fog zone of the Atacama are extraordinary in their geometry. Consider the candelabra cactus, the Echinopsis atacamensis, which grows in the transition zone between the coast and the high plateau. It rises in tall, ribbed columns, sometimes reaching 8 or 9 meters in height, its surface covered in long, dense spines. Those spines are not primarily defensive structures, though they serve that purpose too. They are fog collectors. Each spine is tapered to a fine point, and the geometry of that taper matters enormously. When a fog droplet encounters a spine, it adheres near the tip where the surface is narrowest. As more droplets join it, the growing water droplet is gradually pulled by gravity toward the base of the spine, where it meets the cactus body and runs downward toward the roots. The cactus has evolved a miniature drainage system built entirely from its own surface structure. The Loretta, a plant that looks from a distance like a rounded green cushion pressed against the rock, uses a different strategy. It grows in dense, compact mounds, its surface so tightly packed with tiny leaves that it barely looks like a plant at all. Early travelers sometimes mistook it for moss or even for a green rock. This compactness serves the same fog harvesting purpose from a different angle. The dense surface creates a large total area of contact relative to the plant's volume, maximizing the number of droplets that can be intercepted. The inside of the mound stays slightly warmer and more humid than the surrounding air, and the moisture collected on the outer surface is drawn inward through the plant's structure. The Loretta can be extraordinarily old. Individual plants have been dated to thousands of years, and their longevity is partly a function of how efficiently they extract what little moisture the environment offers. Human communities in this region arrived at the same engineering solution through a different route. The indigenous peoples of the Atacama coast had been reading this landscape for millennia, and the Camanchaca was a resource they understood and used. Modern fog harvesting nets, large mesh panels stretched on frames, erected on the ridges where fog is densest, are a formalization of an ancient intuition. The mesh is typically made from a fine polymer netting with a specific thread diameter and spacing chosen to maximize droplet capture. Too fine, and the mesh becomes a solid wall that the air flows around. Too coarse, and most droplets pass through without touching the threads. The optimal geometry sits in between, creating a surface that intercepts as many droplets as possible while still allowing air to flow through and keep delivering more. A well-positioned fog net in a location with consistent Camanchaca can collect several hundred liters of water per day. Some installations in the Chilean coastal range have yielded over 1,000 liters on particularly foggy mornings. This from air that, measured on a rain gauge, registers essentially zero precipitation. The water is there, it is simply too small to fall. The net makes it fall. There is something philosophically interesting in this. The Atacama does receive moisture, not in the form the sky usually delivers it, not in the form that fills rivers and replenishes groundwater in wetter places, but in a form so diffuse and distributed that it requires a particular kind of attention to notice and gather it. The desert rewards patience and fine-grained awareness. It punishes the assumption that resources arrive in obvious ways. The Chinchorro people, whom we will meet more fully in the next chapter, lived on this coast for thousands of years, and the Camanchaca was part of their world. They would have known which ridges caught the fog most reliably, which mornings brought it deepest inland, which plants dripped most freely after a foggy night. This knowledge was not written down. It was held in the body, passed through generations, encoded in the choices of where to settle and how to move through the landscape across the seasons. The fog arrives each morning before the sun is fully up, quiet and grey, moving inland like something that has been travelling all night across the cold ocean. It settles on the spines of the cactus and the faces of the rocks. It condenses on the threads of the fob nets, running downward in thin rivulets. It deposits itself in the soil in quantities too small to measure with ordinary instruments, but large enough, over time, to make the difference between a landscape with life and a landscape without it. And then the sun rises higher, the temperature inversion weakens slightly, the fob begins to thin and lift, and by mid-morning it is gone. The day is dry again. The desert resumes its ancient practiced stillness. But something has been left behind, a thin film of moisture on every surface that faced the sea, a quiet gift from the cold ocean to the parched land, delivered not as rain but as something gentler and more patient. We have been talking about the Atacama as though it is simply a physical place, a collection of geological forces and atmospheric systems and extreme chemistry. And it is all of those things. But it is also, and has been for a very long time, a place where people lived. Not visited, not passed through, lived. Built families and communities and traditions and ways of understanding the world across a span of time so long that it makes most of what we call history look like a brief afternoon. The Chinchorro people inhabited the coast of the Atacama from approximately 8,000 years before the Common Era, roughly 10,000 years ago, until around 500 years before the Common Era. That is a continuous human presence lasting somewhere between 7,000 and 8,000 years. To put that in proportion, the entirety of ancient Egyptian civilization, from the first dynasty to the fall of Cleopatra, spans roughly 3,000 years. They were not farmers. The hyper-arid desert interior offered little for agriculture, and the Chinchorro were wise enough not to insist on it. Instead, they oriented themselves toward the sea. The cold, upwelled water from the deep ocean carries enormous quantities of nutrients to the surface, feeding blooms of phytoplankton, which in turn support vast populations of fish, shellfish, sea lions, and seabirds. The Chinchorro fished with hooks made from shell and bone, harvested shellfish from the tidal rocks, hunted sea lions, and gathered plant materials from the narrow, fog-watered zone along the coast. The ocean gave them what the desert could not. They left behind many things, tools, middens, the remnants of settlements, but what they left behind that has drawn the attention of the world is their dead. The Chinchorro developed the oldest known tradition of intentional mummification in human history. Their earliest artificially preserved bodies date to around 5,050 years before the Common Era, which means they were practicing this art approximately 2,000 years before the first Egyptian mummies were prepared. The discovery of this fact, when it was established by careful archaeological dating in the late 20th century, required a significant reorientation of how scholars thought about the origins of complex mortuary practice. Mummification had been assumed to be an Egyptian innovation, a product of a highly organized state society with elaborate religious beliefs about the afterlife. The Chinchorro were a small coastal fishing community with no writing, no cities, no centralized government, and yet they had developed a mortuary technology of extraordinary complexity and care. The most celebrated of the Chinchorro mummification styles is the black mummy technique, and it is worth describing in genuine detail, because the detail is where the care becomes visible. When a Chinchorro person died, the body was not buried intact. Instead, it was carefully disassembled. The skin was removed and set aside. The soft internal tissues, organs, muscle, fat, were extracted from the body cavity and from the limbs. What remained were the bones, cleaned and dried. Those bones were then reinforced. Sticks were inserted into the long bones of the arms and legs to provide structural support, and plant fibers, often reeds or grasses, were used to bind the skeleton together, creating a framework that could hold the body's shape even after all the soft tissue was gone. Then the body was rebuilt. Clay was packed around the reinforced skeleton, modeling the contours of the original body, the shape of the muscles, the roundness of the face, the form of the torso. The original skin, dried and preserved, was laid back over this clay form and stitched into place. Hair was reattached. A clay mask was sometimes modeled over the face, with openings for the eyes and mouth, and then the entire surface was coated with a paste made from manganese, a dark metallic mineral found in the local environment, which dried to a deep, even black finish. The result was a figure that was simultaneously the original person and a constructed representation of them. Not quite a body, not quite a statue, something in between, a presence maintained through enormous effort, kept among the living. Why did the Chinchorro do this? We cannot know with certainty because they left no written records, but there is a compelling hypothesis rooted in the desert environment itself. In the extremely dry conditions of the Atacama coast, bodies buried in the shallow soil did not decay in the way they would elsewhere. The aridity preserved them naturally. A person buried in the desert sand might, after some time, be uncovered by wind erosion or animal disturbance, and when uncovered, they would look almost as they did in life, desiccated, dried, but recognizable, intact. It is possible, and many researchers find this persuasive, that the Chinchorro observed this accidental preservation and found meaning in it. Perhaps accidental exposure of preserved bodies prompted a decision to formalize the process, to take deliberate control of what the desert was doing on its own, to choose preservation rather than simply receive it, to transform an accident of the environment into an act of intention and love. If this is right, then the Chinchorro mummification tradition is not an import from some more sophisticated culture and not a product of religious doctrine developed in isolation. It is a direct response to this specific landscape, an art form born from the Atacama itself, from its dryness, its preserving quality, its tendency to hold things in the state they were left. The desert did not rot its dead, and so the Chinchorro chose to keep them. The mummies were not stored away in sealed tombs. Evidence suggests they were kept among the living community, brought out for ceremonies, perhaps consulted in times of difficulty, treated as participants in ongoing social life rather than as remnants of the past. The mineral environment of the Atacama shaped the Chinchorro in other ways too. The salt flats provided a natural preservative. Sodium chloride, the same salt we use to cure meat, was abundant in the soil and could be used to dry and preserve food and materials. The nitrate-rich soils, which would later become the basis of a global fertilizer industry, were a visible feature of the landscape, white crusts and deposits on the surface, sometimes meters thick, evidence of the desert's extraordinary chemical concentration. Copper deposits colored the rock faces in shades of green and blue, and copper compounds stained the tools the Chinchorro made from local stone. The manganese they used to coat their black mummies was gathered from deposits in the surrounding hills, a dark metallic mineral whose deep color must have seemed significant, perhaps associated with darkness, with permanence, with the night sky. The Chinchorro's world was a world of intensely concentrated materials, where a wetter environment would have dissolved and dispersed its minerals through groundwater and rivers. The Atacama held them in place, concentrated them, made them available in forms and quantities that would have been invisible elsewhere. The people who lived here for 8,000 years were shaped by this concentration, and they shaped the landscape in return, leaving behind middens and settlement sites and, most remarkably, the preserved bodies of their dead, a record of human life in one of the most extreme environments on Earth. In 2021, the Chinchorro settlements and their mummification tradition were inscribed on the UNESCO World Heritage List. It was a recognition, quiet and significant, of something that had been true for a very long time, that this desert, which seems to resist life at every turn, has also been, for people willing to understand it on its own terms, a home. In the high interior of the Atacama, above the fog zone and the coastal settlements, above the ancient valleys where the Chinchorro gathered salt for their preparations, the landscape opens into something vast and white and almost impossible to look at directly in full sun. The salaries, the salt flats, stretch across the plateau in plains that can extend for hundreds of square kilometers, their surfaces so flat and so reflective that on clear days they mirror the sky above them with an almost perfect fidelity. Standing at the edge of one is like standing at the edge of a frozen sea that has forgotten how to melt. They are not frozen. They are the remains of something that evaporated. To understand what a salar is, you need to imagine the Atacama not as it is now, but as it was millions of years ago during wetter periods in Earth's history, when the same geological forces that built the Andes were still dramatically reshaping the landscape. The high plateau of the Atacama is internally drained, a technical term meaning that the rivers and streams that flow across it have nowhere to go. They do not reach the ocean. Instead, they flow into basins, enclosed valleys with no exit, where the water accumulates. In a wetter climate, these basins filled with lakes. Some of them were enormous. Ancient lakes covering areas measured in thousands of square kilometers, fed by rivers carrying dissolved minerals from the surrounding volcanic rocks. Over time, as the climate dried and the 3 atmospheric locks tightened, those lakes began to shrink, and as they shrank, something important happened to their chemistry. Water is an extraordinarily good solvent. As it flows over and through volcanic rock, it dissolves minerals from those rocks, pulling ions of sodium, potassium, magnesium, lithium, chloride, sulfate, and carbonate into solution and carrying them along. In a lake that is connected to the ocean or to a river system that reaches the sea, those dissolved minerals are eventually exported, carried away and diluted into the vast volume of the ocean. But in a closed basin with no exit, they stay. The water evaporates. Water molecules at the surface gain enough energy from sunlight to escape into the air, but the dissolved ions cannot evaporate. They are left behind, becoming progressively more concentrated in the remaining water. This is a process that can be understood at the molecular level. Imagine a liter of water containing a small number of dissolved sodium ions and chloride ions moving freely through the liquid. As water molecules evaporate and the volume of the liquid decreases, those same ions are now moving through a smaller volume. At some point, the concentration of a particular ion pair, say sodium and chloride, exceeds a threshold called the solubility limit. This is the point at which the ions can no longer remain dissolved. The attractive forces between the positively charged sodium ions and the negatively charged chloride ions overcome the tendency of the water molecules to keep them separated, and they come together, forming solid crystals of sodium chloride. The salt precipitates out of solution and sinks to the bottom of the lake. Over millions of years, the ancient lakes of the Atacama evaporated almost completely, and their dissolved minerals crystallized into the thick, solid crusts we see today. The salt flats are not simply dried mud. They are deep accumulations of crystallized minerals. Sodium chloride, potassium chloride, magnesium sulfate, and many others laid down layer by layer as ancient lake waters concentrated and precipitated. In some places, the salt crust is several meters thick. Beneath it, in many salares, a brine still exists, a liquid so concentrated with dissolved minerals that it barely qualifies as water in any ordinary sense. And in that brine, and in the crusts above it, is lithium. Lithium is a light metal, the third element in the periodic table, with an atomic number of 3 and a mass so low that it is the least dense solid element that exists. In nature, it occurs almost exclusively as part of dissolved compounds rather than as pure metal. And the Atacama salares contain some of the highest concentrations of dissolved lithium on Earth. The Salar de Atacama, the largest salt flat in Chile, holds roughly a quarter of the world's known lithium reserves. Why here? The answer goes back to the volcanic rocks of the Andes. Volcanic rocks, particularly the types formed by the kind of intense subduction, volcanism, that built the Andes, tend to be relatively rich in lithium. When ancient rainwater fell on these rocks and flowed across them, it dissolved lithium ions from the rock's mineral structure and carried them downslope. Because the Atacama basins are closed drainage systems, that lithium-bearing water had nowhere to go except into the lakes, and from the lakes it could only leave by evaporation. Over geological time, millions of years of this process concentrated the lithium to extraordinary levels. The brine beneath the Salar de Atacama contains lithium at concentrations hundreds of times higher than typical seawater. The extraction of lithium from these brines is relatively straightforward. In principle, brine is pumped to the surface and spread across large, shallow evaporation ponds where sunlight does the work of concentrating the lithium further until it can be processed into lithium carbonate or lithium hydroxide. These compounds are then used in the manufacture of rechargeable batteries, the same batteries that power electric vehicles, laptops, and mobile phones. The Atacama's ancient patient chemistry is now embedded in the technology of the modern world. But the story of the Atacama's mineral wealth did not begin with lithium. A century and a half ago, the desert's most valuable product was something else entirely: sodium nitrate, a mineral that occurs in thick deposits across the northern Atacama, the product of the same extreme aridity that prevents the nitrates from being dissolved and washed away. Before the development of synthetic fertilizers in the early 20th century, nitrates were essential to agriculture. Nitrogen is a critical component of amino acids and proteins, and plants need it to grow. Most of the nitrogen in the atmosphere is locked in a form that plants cannot use directly. 2 nitrogen atoms bonded so tightly to each other that they require enormous energy to break apart. Nitrate, in which a nitrogen atom is bonded to 3 oxygen atoms, is a form that plants can absorb through their roots. Before humans learned to make nitrates synthetically, the world's agricultural nitrogen came from organic sources, animal manure, composted material, and from natural nitrate deposits. The Atacama held the world's largest known deposits of natural sodium nitrate, and in the late 19th and early 20th centuries, mining these deposits made Chile one of the wealthiest countries in South America. The nitrate towns that rose from the desert in this era were extraordinary places. Humberstone and Santa Laura, now preserved as ghost towns and UNESCO World Heritage Sites, were self-contained communities built in the middle of absolute aridity, with theatres, swimming pools, schools and churches, all sustained by the wealth extracted from the white mineral crust of the desert floor. Thousands of workers, many of them migrants from other parts of South America and from Europe, lived and worked in these towns, processing nitrate ore in the brutal heat of the Atacama summer. When Fritz Haber and Karl Bosch developed the industrial process for synthesizing ammonia from atmospheric nitrogen in the early 20th century, creating a way to produce fertilizer without mining natural deposits, the nitrate industry collapsed almost overnight. The desert reclaimed the edges of the settlements, and the wind moved through the abandoned theaters and the empty swimming pools, carrying dust from the salt flats. The desert had been there before the towns arrived. It was still there after they left, patient, dry, ancient, and full of chemistry that the world had not yet found a use for. Now it is lithium. And in the brine beneath the salt flats, the lithium waits, concentrated by millions of years of evaporation, held in the slow, cold dark beneath the white crust, as patient as everything else in this landscape. If you were to take a handful of soil from the hyper-arid core of the Atacama and examine it under a microscope, you might see very little. Mineral grains, a few dust particles, perhaps some fragments of organic material so old and degraded that they barely register as having once been alive. For a long time, scientists looking at this soil reached a conclusion that seemed reasonable given the extreme conditions. The hyper-arid core was, for practical purposes, sterile. Not completely lifeless, perhaps, but so close to it that the distinction barely mattered. That conclusion has been steadily, quietly dismantled over the past decade and a half, and what has replaced it is something considerably more interesting. To understand what has been found in the Atacama's soils, it helps first to think carefully about what life actually requires. We tend to say that life needs water. This is true, in a sense, but it is not precise enough. What life needs, more specifically, is liquid water. Water in a state where molecules can move freely, carrying dissolved nutrients, enabling the chemical reactions of metabolism, allowing molecules to diffuse across cell membranes. The distinction matters because water can be present in an environment in ways that are not available to cells. It can be frozen. It can be bound tightly to mineral surfaces, held so firmly that it cannot move freely or participate in biological chemistry. It can be so scarce that cells cannot maintain the internal water pressure they need to function. The hyper-arid core of the Atacama sits at or beyond the edge of what liquid water can sustain, and yet something is living there. The 2015 and 2017 findings about rainfall and microbial death are among the most counterintuitive results to come out of Atacama research, and they are worth dwelling on. In those studies, scientists examined what happened to the microbial communities in the hyper-arid core during and after rare rainfall events, occasions when enough rain fell to create temporary pools and wet soil across the surface. The expectation, based on ordinary assumptions about life and water, was that the rain would be beneficial. More water means more life. That is how it works almost everywhere else. In the Atacama's hyper-arid core, the opposite was true. The rainfall killed a significant fraction of the microbial communities, not because the water was toxic, but because of a process called osmotic shock. Osmosis is the movement of water molecules across a membrane from a region of low solute concentration to a region of high solute concentration. The water effectively moves toward where there is more dissolved material in an attempt to equalize concentrations on both sides. Cells rely on osmosis to maintain their internal water content. They pump ions in and out across their membranes to control the concentration inside the cell, which in turn controls how much water moves in or out. The microbes of the hyper-arid Atacama had adapted over millions of years to an environment where the external water activity, the effective concentration of freely available water molecules, was extraordinarily low. To survive in this environment, they had evolved internal chemistry calibrated to that near-zero water availability. Their cell membranes, their ion pumps, their metabolic processes, all were tuned for a world where water was almost absent. When rain fell, it flooded the surface with liquid water. The external water activity suddenly jumped from near zero to relatively high. The concentration gradient across the cell membrane reversed or changed dramatically. Water rushed into the cells far faster than the cells could manage, driven by osmotic pressure. The cells swelled. Their membranes were placed under tension. They were not built to withstand. Many of them ruptured. The rain was not life-giving. It was, for these organisms, a catastrophic flood of something they had never been built to handle in those quantities. This finding reframes something important about the relationship between life and its environment. Organisms do not simply prefer certain conditions. They become so finely calibrated to those conditions that departing from them in either direction can be lethal. The hyperarid Atacama microbes were not merely tolerating their extreme environment, they were dependent on it. But where did the survivors go? And where were the microbes living when the surface was too harsh even for them? In July 2024, a research team led by scientists from GFZ Potsdam published findings from a systematic excavation of Atacama soil cores going much deeper than previous studies had attempted. They found, at a depth of 4 meters below the surface, rich and diverse bacterial communities, far more abundant and metabolically active than anything found at the surface or in the first meter of soil. 4 meters is a significant depth. At that depth, the daily temperature swings that make the surface so challenging, from near freezing at night to over 30 degrees in the afternoon, are completely absent. Temperature is stable. The extreme ultraviolet radiation that bathes the surface, partially responsible for the surface's hostility to life, does not penetrate to that depth, and crucially, there is slightly more moisture at depth. Not much, but enough. Water moves slowly downward through the soil profile, and at 4 meters it accumulates in minute quantities in the spaces between mineral grains, held there by capillary forces rather than draining away. It is not much. But for organisms adapted to the limit of what water can sustain, it is enough. The researchers used a novel DNA extraction method to distinguish between intracellular DNA inside living cells, and extracellular DNA, which is genetic material released from dead cells and persisting in the soil. This distinction matters enormously. Soil contains enormous quantities of genetic material from organisms that are no longer alive. A kind of material from organisms that are no longer alive. Previous studies that simply extracted all DNA from Atacama soil were, in part, reading from this graveyard and potentially overestimating the diversity and abundance of living organisms. By separating intracellular from extracellular DNA, the 2024 team could identify which genetic signals came from genuinely living cells. What they found at 4 meters depth included bacteria from groups called Acidimicrobia and Geodermatophylaceae, organisms with a demonstrated capacity for tolerating wide temperature swings, high radiation, and extremely low organic carbon. These are generalist survivors. They appear to play roles in the slow cycling of carbon and nitrogen in the deep soil, fixing atmospheric nitrogen into forms that other organisms can use, oxidizing minerals, performing the slow metabolic work that, over geological time, shapes the chemistry of the soil above them. Life at 4 meters depth is not fast. It is not abundant by the standards of a garden soil or a forest floor. But it is real. It is active, and it has been there in some form for a very long time. And then there is the 2026 finding, which is perhaps the most remarkable of all. Chilean scientists from the University of Chile announced, in April of that year, the discovery of bacteria in the Atacama that appeared to metabolize gamma radiation and cosmic rays directly into chemical energy. not sunlight, not organic molecules, not hydrogen or sulfur compounds. To understand what this means, it helps to think about what radiation actually does to matter. Gamma radiation is a form of electromagnetic energy, very high frequency, very high energy photons. When a gamma ray or a cosmic ray particle passes through matter, it does not simply heat it or illuminate it the way visible light does. It has enough energy to knock electrons loose from atoms and molecules. An atom that has lost an electron is called an ion, and the process is called ionization. In living tissue, ionization causes damage. It disrupts DNA, breaks chemical bonds, generates unstable molecules called free radicals that can damage cell structures. This is why high doses of radiation are harmful to most living things. But ionization is also, in a sense, the creation of an energy gradient. When an electron is knocked loose from a molecule, it is a high-energy electron. It has received energy from the radiation. If an organism can capture that electron, channel it through a series of controlled chemical reactions, and use the energy it carries to drive metabolic work, then radiation is not simply a damaging force. It is a power source. This is what the 2026 Atacama bacteria appear to be doing. They are capturing the energy deposited by ionizing radiation, the way plants capture energy from photons of visible light, and using it to drive the synthesis of the molecules they need to survive. It is a form of chemosynthesis, a word for any metabolic strategy that derives energy from chemical reactions rather than from sunlight. But whereas other chemosynthetic organisms use chemical energy from their environment, hydrogen sulfide near hydrothermal vents, for example, these bacteria appear to use the energy deposited by radiation directly. The Atacama is an ideal environment for this strategy because the desert receives approximately double the cosmic radiation of lower altitude environments. The combination of high altitude, reducing the protective effect of the atmosphere, and the extremely low cloud cover, removing the additional shielding that clouds provide, means that the surface of the Atacama is bathed in radiation at intensities that would be harmful to most organisms. For organisms that can use that radiation as an energy source, the Atacama is not a hostile environment. It is a richly provisioned one. The implications of this extend well beyond the Atacama itself. If life can metabolize ionizing radiation as an energy source, then the range of environments in the universe where life might persist expands considerably. Radiation is ubiquitous in space. Planetary surfaces without thick atmospheres receive it in abundance. The discovery that at least some organisms on Earth can not only tolerate but actively exploit radiation as a metabolic resource is a significant revision of what we think life requires. The Atacama continues to be, as it has been for decades, one of the most important natural laboratories for astrobiology on Earth. Not because it resembles some other planet perfectly, but because it has pushed life to extremes that reveal what life truly is, what it absolutely requires, what it can do without, and what it can, given enough time and pressure, learn to use. The same forces that make the Atacama so hostile to life on its surface make it, paradoxically, the finest place on Earth from which to look outward. The aridity, the altitude, the absence of cloud, all of it, taken together, creates a window in the atmosphere so clear and so stable that astronomers from around the world have spent billions of dollars and decades of effort building their most sensitive instruments here. To understand why the Atacama matters so much to astronomy, you need to think about what stands between a telescope and the universe it is trying to observe. The Earth's atmosphere is not simply a layer of air. It is a complex mixture of gases, each with its own optical properties, each interacting differently with the various wavelengths of light that travel through it. Visible light, the narrow band of wavelengths that our eyes can detect, passes through the atmosphere relatively well, which is why we can see the stars at all. But the universe does not communicate only in visible light. Stars, gas clouds, forming planets, distant galaxies, they emit energy across the entire electromagnetic spectrum, from long wavelength radio waves at one end to very short wavelength gamma rays at the other. And much of that spectrum is blocked or distorted by the atmosphere before it can reach the ground. Water vapor is one of the most significant culprits. Water molecules are very effective at absorbing certain wavelengths of light, particularly in the infrared, the range of wavelengths just beyond the red end of visible light, and in the millimeter and submillimeter radio range. When an infrared photon traveling from a distant star encounters a water molecule in the atmosphere, it is absorbed, and its energy is converted to heat in the atmosphere. The photon never reaches the detector. This is not a minor inconvenience. Enormous amounts of information about the universe are carried in infrared and radio wavelengths. The temperature of a dust cloud can be read from its infrared emission. The chemical composition of an interstellar gas cloud can be determined from the specific radio frequencies emitted by its molecules. The earliest stages of star formation, when a collapsing gas cloud is still shrouded in dust that blocks visible light, can be observed in infrared. The cosmic microwave background. The faint glow of radiation left over from the early universe is most clearly detected in the millimeter radio range. All of this information is accessible only if the atmosphere between the telescope and the sky is as dry as possible. In the hyper-arid core of the Atacama, at altitudes of 4,000 to 5,000 meters, the column of water vapor above an observer is sometimes as little as a millimeter or two in total depth, meaning that if you could condense all the water vapor in the entire atmosphere above you into a liquid layer, it would be less than 2 millimeters deep. This is among the lowest water vapor levels found anywhere on Earth's surface. The atmosphere is, for practical purposes, transparent to the wavelengths that water vapor usually absorbs. The ALMA Observatory, the Atacama Large Millimeter Submillimeter Array, was built to exploit precisely this quality. ALMA is not a single telescope. It is 66 individual radio antennae, each a large dish between 7 and 12 meters across, spread across the Shajnantor Plateau at an altitude of around 5,000 meters. The antennae can be arranged in different configurations, spread across distances of up to 16 kilometers. The principle that makes ALMA extraordinary is called interferometry, and it is worth understanding properly. A single telescope's ability to distinguish fine detail, its resolving power, depends on the diameter of its collecting surface. A larger dish can separate two closely spaced sources of light or radio waves that a smaller dish would blur together into one. This is because the wave nature of light means that a larger aperture collects the incoming waves across a wider front, allowing finer details of their structure to be resolved. But there is a practical limit to how large a single dish can be built. Engineering constraints, the sheer weight and cost of a massive structure. Interferometry bypasses this limit. Instead of one large dish, you build many smaller dishes separated by large distances. The signals collected by each dish are recorded with extraordinarily precise timestamps and then combined electronically. When signals from two separate dishes are combined, the interference pattern between them, the way the wave crests and troughs from the two signals align or cancel, carries information equivalent to what a single dish as large as the distance between them would collect. ALMA's antennae, spread over 16 kilometers, effectively simulate a single dish 16 kilometers wide. No structure of that size could ever be built, but the mathematics of wave interference allows the same resolving power to be achieved with 66 smaller dishes and a great deal of computing. What ALMA has revealed with this resolving power is extraordinary. In 2014, it captured images of the dust disk surrounding a young star called HL Tauri about 450 light-years away. The disk showed a series of concentric rings and gaps, alternating bright and dark bands in the dust that indicated planets were already forming, clearing lanes through the disk as they orbited. The star was less than 1 million years old. Before Alma, it was assumed that planet formation was a slow process that took many millions of years to produce visible structure. The HL Tauri images suggested it could begin within the first 1 million years of a star's life. Alma has also detected the chemical signatures of complex organic molecules drifting in interstellar clouds, molecules with multiple carbon atoms, some of them precursors to the amino acids that form proteins. They are widespread, found in cloud after cloud across the galaxy, suggesting that the chemical building blocks of life are being assembled in space long before any planet forms to receive them. The Very Large Telescope at the Paranal Observatory, located on a mountain called Cerro Paranal in the coastal Atacama at an altitude of about 2,600 meters, is a different kind of instrument, an optical and infrared telescope operating at the wavelengths of visible and near-infrared light. It consists of 4 main telescopes, each with an 8-meter primary mirror, and 4 smaller auxiliary telescopes, all capable of operating together as an interferometer in the same way Alma's dishes do. The resolving power of the Very Large Telescope is such that, in principle, it could distinguish the 2 headlights of a car parked on the surface of the moon as 2 separate points of light rather than one. This is not a figure of speech. It is a quantitative statement about the instrument's angular resolution, derived from the physics of the mirror size and the wavelength of light being observed. At that level of precision, the instrument has resolved the surfaces of nearby giant stars, not just points of light, but actual disks with visible surface features. It has directly imaged planets orbiting other stars. It has measured the orbits of stars at the center of our galaxy so precisely that the only explanation for those orbits is the presence of a supermassive black hole, an object about 4 million times the mass of our Sun, at the galactic center. And at night, above all of these instruments, the sky that makes them possible spreads out in a way that is difficult to describe to someone who has only ever seen it from a city. The Milky Way on a clear night is not a faint smear across the sky. It is a dense, complex, 3-dimensional structure. Clouds of stars, dark lanes of dust, the bright core of the galaxy itself glowing like an ember. Ancient cultures across the Andes developed astronomical traditions based on the dark patches in the Milky Way as well as the bright stars, recognizing the dark nebulae, the clouds of dust that block starlight, as shapes worthy of naming and myth. In the Atacama sky, those dark shapes are as vivid as the stars themselves. The same quality that makes this desert nearly lifeless on its surface, the absence of water, the absence of cloud, the absence of almost everything that most living things need, is the quality that makes it humanity's clearest eye on the deep universe. The desert's emptiness is the instrument's precision. The silence below is the signal above. The sun sets quickly in the Atacama. There is no long, humid twilight of the kind you might know from a coastal city at lower latitudes, where the sky stays pale and warm for an hour after the disk has dropped below the horizon. Here, the air is too dry to scatter much light, too thin to hold the warmth, and the transition from day to evening is abrupt and clean. One moment the plateau is amber and gold, then it is grey. Then the stars appear, not one by one but all at once, as though a door has been opened in the sky. And the cold comes with them. During the day, the Atacama's high-altitude surface absorbs solar energy. The dark volcanic rocks grow warm to the touch. The salt flats reflect light back upward and stay cooler, but the soil and stone of the plateau heat through the long, cloudless day. When the sun sets, that stored heat begins to radiate away. In a humid environment, the water vapor in the air would absorb much of this outgoing radiation and re-emit some of it back toward the surface, slowing the cooling. The same mechanism that makes tropical nights warm and coastal cities milder than inland ones. In the Atacama, there is almost no water vapor to do this work. The heat radiates freely upward, into the thin air, into the clear sky, into space. The ground cools rapidly. The air above it cools with it. By midnight, temperatures that reach 20 degrees or more in the afternoon may have dropped to near or below freezing. This rapid cooling is not merely a meteorological fact. It is a mirror of something that happens in your own body each night as you move towards sleep. Your core body temperature follows a daily rhythm, rising slightly through the afternoon and then falling in the evening hours. This drop in core temperature is not a consequence of sleep. It is a signal that prepares the brain for sleep. The hypothalamus, a small region at the base of the brain that coordinates many of the body's internal rhythms, reads the falling temperature and uses it as one of several cues to shift the brain toward the deeper, slower patterns of activity associated with rest. Heat is actively moved from the body's core to its periphery, to the hands and feet, and radiated away from the skin surface. Your feet and hands grow warmer as your core grows cooler, and the brain interprets this redistribution as the approach of night. The Atacama cools the same way and on the same schedule. The plateau sheds its heat into the sky, and the sky receives it and holds nothing back. By the time the temperature has dropped to its nightly low, the desert is as cold and still as it will ever be, the rocks contracting slightly in the chill, the salt flat cracking with a soft sound in the silence, the air barely moving. The silence of the Atacama at night is a quality that visitors consistently struggle to describe. It is not simply the absence of human noise, though it is that. It is the absence of almost all sound. No wind in tree leaves because there are almost no trees. No water moving because there is almost no water. No insects because the insect populations of the hyperarid core are sparse and quiet. The silence is so complete that it becomes perceptible as a presence, something you can feel against your ears, a depth of quiet that seems to have weight and texture. In this silence, if you listen, you might hear the occasional distant creak of a salt flat expanding or contracting with the temperature change. You might hear, very faintly, the sound of wind crossing a distant ridge. And overhead the stars are so numerous and so bright that the Milky Way casts a faint, diffuse shadow on the ground, a phenomenon so unfamiliar to most people that it takes a moment to understand what you are seeing. The shadow of the galaxy, the light of 100 billion stars, arriving after journeys of thousands of light years, intense enough to throw a faint darkness behind a rock. The oldest threads of this journey are still present in the night air. The 15 million years of silence, the hyper-arid core sitting unchanged through deep geological time, through the rise of the Andes and the cooling of the Humboldt Current and the slow concentration of lithium in the basins below. The fog that will arrive again before dawn, rolling in from the cold sea, condensing on the spines of the cactus, depositing its patient gift of water on every surface that faces west. The microbes resting 4 meters below the ground, their metabolisms running at a pace too slow to call active in any ordinary sense, but real, genuinely alive, genuinely persisting in the patient dark beneath the salt. The Chinchorro are gone from this coast in the sense that their civilization has passed, but the mummies they made, the black figures with their clay faces and their manganese skin, are still here, held in museums and archives, preserved by the same aridity that preserved the bodies in the first place. The desert kept what the Chinchorro entrusted to it. It keeps things. That is what it does. And above, the antennae of Alma stand on the Chajnantor plateau, their dishes tilted toward various points in the sky, collecting radio waves from gas clouds where stars are forming, from the dusty disks where planets are assembling themselves, from the chemical signatures of organic molecules drifting in the cold dark between the stars. The instruments are quiet in the way the desert is quiet, not inactive, but deeply, attentively still. The night deepens, the temperature drops further, The salt flat contracts again with a sound like a distant, soft percussion. The stars wheel slowly overhead, the same stars that the Chinchorro watched from this coast, the same stars that the Inca navigated by, the same stars that the first astronomers who came here with their telescopes looked up at and understood for the first time just how extraordinary this sky truly was. If you are still awake, you don't need to be. The desert does not require your attention. It has been here without you for 15 million years. It will be here long after tonight. It does not need to be witnessed to be real. It simply is, ancient and dry and patient, the oldest silence on earth, holding its minerals and its microbes and its fog and its stars in the same unhurried stillness it has always held them. Your body is cooling now, the way the plateau cools, heat moving from your core outward, your hands perhaps growing warmer as your center grows quieter. The brain is beginning its slow, heavy drift toward the deeper work of the night. The day is already somewhere far behind you, as distant as the Amazon moisture that the Andes turned back millions of years ago. The fog will come again before dawn. The microbes below the surface will continue their slow, patient chemistry. The antennae on the plateau will keep listening. And the desert will keep being old. Sleep now, if you're ready. The silence has been here all along, waiting for you.